So let's say we have a Markov chain, and it has 3 states.
Okay.
For simplicity, I'll just call them, 1. I'll just erase my own work with the marker. 2 and 3. That be seen? Yeah, kind of. There's just going to be 3 states.
Okay.
If we want to, we can draw them. Just going to draw them as 3 circles. 1, 2, and 3.
Okay.
Now, a couple of very important properties of Markov chains I think are best shown by an illustration like this.
Okay.
So let's talk about these conditional probabilities and how they actually work.
Okay.
In this whole, chain, you can think of the transition probabilities in 9 different ways. There's 9 different probabilities you can think of here, right? I'm going to start writing them out, and hopefully you get the gist of the pattern. So the first one is if you're at 0 at time step 0, if you're 1 at time step 0, you can just stay at 1.
Okay.
Perhaps that's something we want to allow. You could also go to 2. That should be a 1. You could also go to 2, or you could go to 3. And similarly, for all of the other variables, you have the same sort of set, just with this last condition changed to 2 or 3 for the different states.
Okay.
There's essentially 9 possible connections you could have here.
Okay. So, sure, maybe it would be helpful if we go back a little bit. What is the sample space for each of these 3 random variables?
No, these are.
Oh, sorry.
This is the sample space.
Oh, this is the sample. I'm sorry. I'm sorry. Okay. Okay. I'm sorry. Wow. That was a. Glad that we clarified that. Okay, so that is the sample space.
That's the sample space.
So a random variable could take on each of these. One of these three values. Okay.
At a time step, it can be one of these values. It could be 1, 2. It could be 3.
Right. Okay. So at one state, it could take on one of these 3 values. In the next state, it could take on one of these 3 values. And so 3 times 3 gives us 9 possible values.
Yeah, exactly.
9 possible different transitions.
Yes, exactly.
Right. Okay. Good.
Now, not all of these need to be actual positive values. Some of them could be 0. You
Right.
could have the case where we say, you know what, if it's at 1, it doesn't go back to 1.
Right. Okay.
It can only go positively or negatively.
Okay. It's okay. It's okay.
How do we trigger that?
The light's gonna come back on. It's okay.
Someone will leave.
Yeah. That's why we have a little bit of light here. Just see. Yeah. I knew it was gonna come back on. Yeah.
Someone will leave. There's people still here.
Yeah.
No, this is the sample space. I suppose I should have made that clear when I was writing it out.
It's okay.
So at any given time step, it can be any of these values.
Right.
And not all of these, once again, need to be positive. They could be any value.
They could be 0 or positive.
0 positive.
Right.
And you have the restriction, of course, that if I took the sum of all of these 3, conditioned on the same initial value, it needs to equal 1.
That's right.
Because you know when you look at it again, it's going to have gone somewhere.
Yes.
It's not going to end. You're not going to look at the chain and it doesn't exist anymore.
Right. So that we're trying to, of course, make sure that we fulfill the Kolmogorov laws of probability.
Yeah.
Right. Okay. Good.
But an easy way to kind of get an idea of what these probabilities are, and rather than having to write out this really cumbersome notation, I'm just going to do this with arrows. So if I draw an arrow from, let's say, 2 to 1, if that can be seen, I'm going to consider that the conditional probability of going to 1 from 2.
Right.
So essentially, Px1 equals 1, given x0 equals 2.
Yes.
And similarly for any other arrows I draw.
Right. Okay.
And then if I write, I don't know, a number beside that, we'll call it 0.1 in this case.
Okay.
That number is going to be the probability of that transition.
Right. Okay.
And now, of course, there are lots of different ways we can connect these points. That one, of course, being the probability of returning to 3.
Right.
And as long as we satisfy those laws of probability, any one of them is equally valid.
Right.
They're a different chain, and they have different behaviors, but any one of them defines a valid Markov chain.
Right. Yes.
Now, if we play around with this for a little while, we're going to recognize there's a couple of different situations that can pop up with any particular point.
Okay.
And these lead to the ideas of communication and classes in a Markov chain.
Okay. Okay.
So let's talk about the idea of communication first of all.
Okay.
Let's focus on just 1 and 2 for the time being.
Okay. Sorry, if we could just quickly interrupt. I realized I said Kolmogorov laws of probability. I think strictly speaking, they are the Kolmogorov axioms of probability. Sorry about that. Okay. Sorry, Chris. Please go ahead.
It's a law by a different name, I suppose. You don't break the law, right?
Yeah.
Let's just look at 1 and 2.
Okay, 1 and 2.
So there's a few different configurations.
Right.
We can imagine that there's no connections between 1 and 2.
Okay. So then that would be 0.
Well, they could still communicate with 3. Yeah, there'd be nothing between 1 and 2, but they still could communicate with 3.
Right.
They could still have arrows between them and 3.
Okay. Okay.
But if you imagine that they don't, let's say that this is the system we have. We have 1, and it only goes back to itself.
Okay.
2 and 3, they happily go back and forth, but there's also a probability that 3 leads to 1.
Okay.
There's no way for me to get from 1 to 2 under this structure.
No, you can't.
You can't go from 1 to 2. You could get from 2 to 1.
Right.
So 2 does go to 1, but there's no communication there.
Right. So what do you mean by communication?
That's a definition. Okay. Essentially, if there is some way that is non-zero to get from one value to another, we say that, that's not communication. What's the technical term for that? There's actually a name for it.
Okay.
I only remember communication, though, because typically the one-directional relationships are much less important.
Okay.
Yeah. If 1 goes to 2, or if 2 goes to 1, but 1 doesn't go to 2, we will say that 1 and 2 don't communicate.
Okay.
However, if instead there's a way for me to get back to 2, even if it's not directly to 2,
okay,
then we say 1 communicates with 2.
Okay. Okay. So communication requires that there is a transition from one to the other, and also in the reverse direction.
Yes.
Right.
It doesn't need to be in one step. It can be in n steps, but as long as there's a positive probability of going back, we say the 2 communicate.
Okay. Okay.
And the important thing about communication is in a Markov chain, communication allows you to actually separate the chain out into different parts.
Okay.
Most importantly, a lot of the stuff we're going to talk about later to do with stationary distributions assumes inherently that all of the states communicate.
Okay. Okay. All right. We'll remember that.
So there's this idea of communication, which is that you can go between 2 states and back.
Okay.
Right? And obviously 2 and 3 communicate because you can just hop back and forth as many times as you want.
Right. Okay. Good.
And by definition, we say that any state can communicate with itself.
Okay.
That's just something we say, even though there may be no positive probability of returning to that state from itself.
Oh, okay. So if the probability of one state going to the same state is 0, we still say that
it communicates with itself.
Oh, okay.
So you could have state 1 over here, and then you could have 2 and 3.
Okay.
So 1 maybe only communicates, or 1 only goes to 2 and 3, but there's no way to get back to 1. So let's say you start the chain at 1. Then at step 2, you're going to be at 2 or 3. You're no longer going to be at 1.
Right. And there's no transition from 3 to 1, so you can't even indirectly go back to itself. Okay.
In this situation, you may in your analysis end up separating these 2 parts out. So you consider this as two independent Markov chains, as it were. You have this first one, which you leave, and then you have a second one you go to.
Right. Okay.
Right? You may think, okay, there's also some probability I come to one and I can communicate with myself. And then you have a question of, well, when do I end up getting to 2 or 3? Like, let's say I start at 1 and there's some probability 1 goes back to itself. What's the probability, or how long does it take until I enter this 2 and 3 relationship? Because I know once I get there, I'm not coming back.
Right. Okay.
When you look at it like this, it allows you to partition Markov chains into these different independent subchains, as it were.
Right. Okay. Okay.
Communication is incredibly important just for getting, I guess, the lay of the land, as it were, to try and figure out how these chains interact and how you can break them apart.
Okay. Okay. Good.
I'm trying to condense stuff a lot here.
No. This is good. I follow what you're saying, and that's the most important thing.